Hello everyone, this is Dr. Sheikh Imambali, Associate Professor in the Department of ECE. In this lesson, I'm going to discuss about introduction of plasmonics, and also I'm going to discuss about the introduction of spoof surface plasmon polaritons. In this lesson, I'm going to introduce about what is a plasmonic and what is the motivation behind to study about the plasmonics and what are the major advantages and applications of plasmonics, and then we'll discuss about what is surface plasmon and what is a spoof surface plasmon polaritons. Coming to the introduction of plasmonics, this plasmonics or plasma, we can call it as it is a quantum of plasma oscillations, and this these are the collective oscillations of electrons in a material. Other words, we can say it as it is a like a wave-like excitation of electrons that can propagate through material. So these plasmons typically existed in materials with high electron densities. So those materials can be semiconductors, metals, or graphenes. So these plasmons are having liquid-like behavior of electrons where the electron oscillate in a coordinated manner. So these plasmons are classified into several types, which includes bulk plasmons, surface plasmons, and spoof surface plasmons. So in the bulk plasmons, whenever we are incidenting the light or electromagnetic wave, so this wave can be propagating parallel to the propagation, so that we can call these bulk plasmons as transfer waves. In case of surface plasmons, whenever we are exciting electromagnetic waves or light, so this is propagate perpendicular to that propagation, and we can call this surface plasmons as longitudinal waves. So bulk plasmons are transfer waves and surface plasmons are longitudinal waves. And coming to the third one, spoof surface plasmons. So the spoof surface plasmons are also known as artificial surface plasmons or artificial engineered grooves or textured textured surface plasmons. So there are various names for these spoof surface plasmons. The basic operation and the introduction of this surface plasmon polaritons. This surface plasmon polaritons are the coupled mode of surface plasmon and also electromagnetic waves propagating along the interface between metal and dielectric. For suppose if here you can see this is the interface of metal surface and the dielectrics. So it is coupling of this metal surface and dielectrics so that this will be propagating in that particular direction, x direction here we can say it. Coming to the localized surface plasmons. So this localized surface plasmons, what it is happened, it confined the electron oscillations in small metallic nanoparticles. This will not propagate, this LSP do not propagate, but they lead intents to make strong electromagnetic field enhancement. So in the figure A, we can see that this is the surface plasmon polaritons of the coordinating system, and in the figure B, we can see that some electron cloud. So this is oscillation. Whenever we are incidenting this light towards this the interface, then the surface plasmon and the electromagnetic waves are coupled together and it will propagate in the particular direction. So the motivation behind this surface plasmon polaritons are these are the gaining more significant research in the biosensing applications, like to detect any biological samples with rapid and accurate and label free detections. And also this SSPP surface plasmon polaritons we can use for sensing capabilities because it is having strong field confinement and which will work in the lower frequencies, less frequency operations, and it will give high sensitivity and selectivity for with low fabrication cost. And also this smooth surface plasmon polaritons are having it can work in terahertz and micro biosensor. So with this we can use for biomedical diagnosis, environmental monitoring, and industry applications. This is the basic motivation of the spoof surface plasmon polaritons. Coming to the advantages and applications of this spoof surface plasmon polaritons. So it is having tunable dispersion. So we can tune this electromagnetic waves or cutoff frequencies with the dispersion relations, and also we can able to enhance the light matter interaction, like we can make strong field confinement, and also we can use this SSPPs for high sensitivity to environment. For suppose if any changes in that environment, we can able to sense by using this SSPP. And applications which includes optoelectronics. With this SSPP, we can make use of optical switches, modulators, and detectors. And also we can use this in the sensing platform, like detect changes in the temperature, pressure, and chemical compositions. Also in quantum computing, the quantum computing process also we can able to use these SSPPs, and metamaterial aspect, we can create some artificial materials by using this SSPPs, and we can work on it. Here in this slide we can able to see this one is a metal epsilon omega, and this one is a dielectric material. So whenever we are incidentting the light at the interface, there is a strong amplitude decay. You can say it as exponentially decay in the both regions. One is in dielectric region and another one in the metal region. Compared to the dielectric region, the decay is less in the metal due to their skin depth and material properties. Okay, so this SSPP is, we can call it as the product of coupling between the EM waves in the dielectric medium. So this is the dielectric medium, and plasma oscillations in the metal. So this is the metal. So in this metal we have the plasma oscillations. So whenever we are coupling the electromagnetic waves which are existing in the dielectric material and also plasma oscillations which is existing in the material, then it can able to propagate along the direction. This is the equation of wave, surface Boltzmann wave number, omega by c, which is omega by c root of epsilon naught 1 epsilon naught omega divided by epsilon naught 1 plus epsilon naught omega. So here epsilon naught 1 is the dielectric medium, epsilon naught omega is the metal. So coming to spoof surface plasmon polaritons at low frequencies. So this spoof surface plasmon polaritons initially introduced by Pendry, John Pendry. So in their research what they did, so this because of the limitations of surface plasmon polaritons, SSPPs, we can make it short, which do not support below the far infrared frequencies due to the absence of strong field confinement. To bring this surface plasmon polaritons to lower frequencies, they have introduced artificial spoof surface plasmon polaritons, or we can call it as spoof surface plasmon polaritons, or textured surface plasmon polaritons. So the lower frequencies, metals are like behaving like perfect electric conductors rather than that optical frequencies. So this is the spoof SSPP structure. So this is the geometrical parameters of this SSPP. This is the electromagnetic field of this SSPP. We can able to see how this spoof surface plasmon polariton is propagating along the interface of both metal and dielectric. So in the figure B, 2B, we can see the dispersion relation of SSPP. So this black one indicated the light line, and this red color curve which is explaining about the spoof surface plasmon polariton curve. We can call it as a dispersion curve or cutoff frequency curve, we can call it as. And in the figure 2C, so this is the 1D corrugated metal surface. So D is the distance between two groups and P is the periodicity of this groups and H is the height of this group. So by varying this geometrical parameters D, P, H, we can make and we can play with this dispersion curve. The basic equations of this SSPP is, so this is the dispersion relation k square c square equal to omega square plus 1 by omega PL square minus omega square 64 a power 4 omega power 4 by pi power 4 d power 4. So this A and D are the geometric properties of that 1D corrugated uh, structure. So K, we can know that is the wave number of the SSPP along with the interface, and omega P is the plasma frequency, C is the velocity of the speed, light speed in the vacuum, and the equation for plasma and cutoff frequency is omega P is pi by C, A into root of epsilon h and mu h. This epsilon h and mu h are the permittivity and permeability of the materials. And also we can see the relationship between the propagation vector and 1D geometry of SSPP structure with this following equation.